All right, here we go. Today is Wednesday, April 11th. We're taking care of notes on the collision model, factors affecting rates of reactions, heterogeneous reactions, equilibrium, dynamic equilibrium, and then we'll finish off with a quick demo. The demo is going to be the milk of magnesia demo, which I'm going to post to YouTube after I post this. Very important today to definitely read and outline chapter 17.1 because chapter 17.1 has to do with what we're doing right now, and I'm only spending enough time to do a brief overview of this. All right. Do intro to equilibrium constant worksheet. That's not going to happen until tomorrow, so don't worry too much about that. Make sure to get this read and outlined first. All right. So chemical equilibrium, here are the goals. We want to be able to describe reversible reactions. We want to understand and define what equilibrium is. We want to understand Le Chatelier's principle. Recognize a system at equilibrium. So you're going to be able to construct what's called a KEQ and also relate how this KEQ value relates to how much product or how much reactant the chemical reaction is going to want to make. We're going to predict the results of making changes that affect the equilibrium position, which we'll be talking about when we talk about Le Chatelier. And then we also want to be able to calculate the equilibrium constant. All right. This looks like a lot, but it's not. The first two bullets we're going to be talking about today, we actually talked about the first one yesterday when we did the lab, the equilibrium lab, which there is makeup data if you missed that. All right, let's get going on this. Le Chatelier we won't do until next week, though. All right, how chemical reactions occur? Well, there's something called the collision model. Basically, the collision model says that in order for molecules to react with each other, they have to touch, they have to collide. That makes a heck of a lot of sense if you've been paying attention, because we know that electrons have to be shared, lost, or gained. So you've got to be able to come close enough to touch, if you're a molecule, to touch another molecule's electrons. So you got to actually touch each other. The rate at which these things, the rate at which reactions occurs depends on, number one, the orientation. So what direction are things hooked up together in, the concentrations, and the temperature. This all relates to the lab yesterday with the pop beads. Two pop beads are put together. They have to be put together end to end. They can't be put together tip to tip. The more pop beads you've got, the quicker you're going to be able to put them together. And then the temperature relates to how hard you have to push the pop beads to get them to stick and snap together. All right. The book talks about it this way. The orientation has to be right, so they have to be lined up side by side according to this diagram. If the bromine had come in and hit the oxygen here, nothing would happen, no chemical reaction. All right. The temperature has to be right, so they have to be moving fast enough. And also, the concentrations have to be, there's not really anything in this picture about concentrations. But it does show that when these two things come together, this bond here between nitrogen and bromine is broken between bromine and bromine forms, and you get this as a final product. Okay. Now, if you think about this for a second, as far as concentrations is concerned, the more of these guys that I've got, the more likely it is that two of them are going to knock into each other side by side like this. It's kind of like thinking about the fact concentration. Where are you more likely to get into a car accident? Assuming all drivers drive the same. Out in the country or in the middle of the city? That's right, in the middle of the city, because when you've got more cars, you're more likely to get in an accident. So if you got more molecules, you're more likely to have a reaction that is going to be favorable, a collision that's going to be favorable and lead to this. Okay. Conditions that affect reaction rates. Concentration is definitely one of them. The more, like we were just saying just a moment ago, the more collisions you've got, the more likely it is that one is going to be favorable. Temperature also is another factor. The reason why, higher temperatures means higher speeds. Higher speeds means more high energy collisions. More high energy collisions means more collisions that are going to break bonds because they're favorable, and more of those mean that the reaction is actually faster. Okay, so it's a chain of events. It's not just because they're moving at higher temperatures. Okay, you'll see this this diagram in the book. Okay. Activation energy is another thing. We've talked about activation energy in the past. Basically, what activation energy is, here, let me back up for a second. Activation energy is the minimum amount of energy required for a reaction to occur. Okay, so there's a certain amount of energy that a reaction needs before it is actually going to happen. This diagram shows you that energy on the y-axis, whether the reaction goes or not on the x. Notice reactants are here, products are over here. There's a certain amount of energy here that is the activation energy. Unless I get this particular amount of energy at a minimum, I'm not going to have a reaction happen because the reaction basically is driving up this hill, this energy hill, and it can't complete until it reaches this peak here. So if it doesn't get exactly that minimum, that amount of energy, it's not going to be able to go over the hill and fall down into the products. All right. Catalysts are substances that speed up a reaction without being consumed. And enzymes are a specific brand of a specific class of catalysts. They're biological catalysts made by living things. But here's the basic idea. Normally, a catalyst is going to need to, normally without a catalyst, a reaction needs a certain amount of energy, this amount right here. If you add a catalyst, though, what a catalyst does, by definition, is it makes things easier. It changes the amount of energy that a reaction needs. So we've got E prime A, so the catalyst's activation energy, which is lower. What that means for somebody that's actually making these products here and trying to sell the products, like plastics, that means that they've got to spend less money because they need less energy in the reaction. All right. Heterogeneous reactions is exactly what it sounds like, and homogeneous are exactly what they sound like. Homogeneous reactions are where the reactants of the products are all in one phase. So, for instance, a liquid and a liquid combine together and they have a chemical reaction. All right. So heterogeneous reactions are where the reactants are in two or more phases. So here, notice we got solid, we got an aqueous, we got a gas, we got an aqueous. We've got two or more right there. Okay. That's about it there. We're going to skip this slide. That's in the book. Something you can read. Just a refresher. Equilibrium condition. The condition of equilibrium is the exact balancing of two processes, one which is opposite the other. So one car going forward, another car going backwards. If you think about a car, drive and reverse are equilibriums. If you do an equal amount of them, well, we'll get to that in a second, but the book talks about the fact that, look, you've got 3 molecules of water evaporating, and here you got 3 molecules of water condensing. This is an example of an equilibrium. Okay. 3 things going up, 3 things coming down. They're the exact opposite of each other. A chemical equilibrium is a dynamic state where the concentration of all reactants and products remain constant. All right, what does that mean? Well, that means that's when you have the reaction, 3 things are going up while 3 things are going down. Notice here, if 3 things go up first and then 3 things come down after, here the situation is they're happening at the exact same time. Okay, so they're going 3 to 3 up and really can't tell the difference. I'm going to skip this slide. Skip this one. All right. This is equilibrium rate. Notice this is very similar to the results you should have gotten in the lab using the makeup data or the data that you did in class. You notice that the one rate comes down while the other rate goes up. So the forward rate is coming down, the reverse rate is coming up. Eventually, they reach a point where they're not going down or they are not going up. Now, I'm not going to say they're at the exact same point because that's not necessarily true. But what is happening is they hit a plateau and they neither go up nor down. So they just go horizontally. That is equilibrium, this horizontal portion right here. Let me show you the data that we got. Here's the data that we got from lab, or that we should have gotten, fairly close to the makeup data. Notice that we're going down, 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 and we reach a point here where we almost have a plateau, a horizontal plateau right there. Same thing's happening here. The reaction is coming up, 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 and we reach a plateau. Now uh, these two graphs are a little bit different from each other, and I want to point this out. The reason why the graph that's on the PowerPoint slide, this graph here, reaches a plateau at the same place is because this is talking about a reaction rate on the y-axis. So as the blue loses one, the pink gains one, loses one, gains one, loses one, gains one. So they're going to be at the same rate, the same exact rate, 20 molecules per second, whatever it happens to be. Up here, this y-axis is not labeled as reaction rate, it is labeled as number of atoms or number of molecules. When you take a molecule and you lose it, you're going to wind up gaining 2 more atoms. So there's a 1 to 2 ratio here. So these two things, unless you get a very specific set of circumstances, are not going to be the same level. And I've never seen them come to the same level with this lab. Okay. So, okay, this is the MOM demo, Malcolm Magnesia demo. I'm going to put that on YouTube separately. That's basically all of the stuff that we went over today in class. Again, don't forget to read and outline chapter 17.1 and 17.2. And I'm going to give you guys the equilibrium constant introduction worksheet tomorrow in class. I think we'll work through that. All right, good luck.